Good day, everyone. Welcome to the Physics and Material Science modules for Introductory Laboratory in Physics class. So this is Mech 1 about measurements. First of all, when we talk about measurements, we're going to talk about precision and accuracy of the measurement. So what are the differences between these two? You could technically explain this by involving archery, and archery also happens to be my hobby, so I like to talk about that. So when you make your shots, it could actually hit in different ways. You could actually get accuracy and precision at the same times, and another thing is you could also miss the target, but then again you could still be precise because your shots are actually clustered around the same spot. Or on the other hand, if you try to aim for the center, you missed it. So that's actually like your lack of accuracy. But it doesn't mean that you could still be. It actually means that you could still be precise when talking about this accuracy versus precision thing. And then again, when you aim towards the center, your shots can still be scattered around, and that's the lack of the precision. And you could also lack both accuracy and precision and then miss the target completely. The thing is, this also happens in a lab. Like whenever you conduct any sort of experiment, you would still run into issues about the errors, and always the errors would actually happen. So every time I make measurements, I would think of my teacher, Ajahn Dusadi, who quoted a book, "To err is human, to describe the error properly is sublime." So technically, every single time you work on something, you want to keep thinking about the errors and figure out where it actually came from and describe it properly when in whatever you do, especially in the laboratory. And we're going to go on to the next. So when we talk about the error, experimental errors happen all the time. So different types would actually incur different kind of error. For example, first type is random and statistical error. This is the error that's affected by precision. It's literally human error, tools limitation, or but then again, like say you have shaky hands, you could actually keep repeating the experiment to correct for this random statistical error. So one thing we're going to be doing a lot today is repeating our experiment and keep doing the measurement until we could actually minimize the error. So the lack of precision, if you compare it with the archery style that I was talking about earlier, would actually have this target and the shots aim towards the center. If you average all this shot, it would actually be clustered around the center, but then again, it actually spread out a little bit. So this spreading is from the lack of precision. So another type of error is systematic error, and this affects the accuracy and it could actually be from the offset of the tools and something that might have gone wrong in the system. So even if your measurement is precise, you could still actually have accuracy problem. Like you see, like the shots scatter actually cluster around, but then again, it completely missed the mark. The reason that it completely missed the mark is because could be like the bow is not well calibrated, or in the sense of measurement, you could actually think of it as a ruler being somewhat broken. It's instead of starting from 0, it starts from 10 centimeters or something. And then again, a bad experiment would be when you actually have existence of both random error and systematic error. So you want to avoid this at all cost and try to make the elimination of both to create a good data collection in order to get some meaningful sense of data for analysis. And another thing that would actually limit our measurement is the tool we're using. For example, if I were to measure this paper clip using a ruler, so the question would be, how long is that paperclip? So to do this estimation, you could actually say, oh, that's a 2.3 something centimeters. I could say, I don't know, it's a little bit more than 2.3. So let's say I make a guess of the last number, or let's say if I call this experiment like I do this measurement and I get the length of 2.3503 centimeters. Would that be over accuracy? Then yeah, because the tools does not provide scale for you in order to read with such precision. So what you can do is, well, this is over precision. Maybe my estimation is, overestimated, and then again, you want to stick to the precision of the tools in order to report the data that's occurrence from this measurement. So what if I say 2.3 centimeters? You can obviously see from this picture that it's more than 2.3, but then again 2.3 would be an under precision kind of representation of this reading, because if you read this number, then you're basically underplaying the accuracy of their tools. So what you could do is basically you can actually make an estimation like this is more than 2.3, so perhaps you could add half a scale more. So half the minimum scale is generally the precision of the tools that you want to use. For example, in this case, ruler, the minimum scale is 1 millimeter or 0.1 centimeters, so you could actually make an estimate of an extra half centimeters. So also, whenever you make such estimation, you want to make the mark to put the underline around the number that you actually estimate, and this would be the result that you could actually report for the measurement done with a ruler. So then again, you get to keep the precision you want, and you don't over-report it, and you don't underplay the precision of the tool. So that is something that you want to report in your report. And so generally, first of all, whenever you hold a tool to measure anything, you want to make sure that you properly represent the data that was read by the tool. So another thing is, another tool that you'll be using today is the Vernier Caliper, and a Vernier Caliper looks like this. It actually has many teeth and the scale that you could actually be reading from, and that would actually have many gaps that are opening, and as you can see that there are A, B, C here, and whenever you move the Vernier Caliper, you could actually use it to read many different things depending on the dimension of the materials which you'll be using today in measuring a piece of cylinder. So then again, like all of A, B, C that you could use to measure any length depending on the proper scale you want to read would actually be represented by the same number. So the next question would be, what would that number be when you want to read it out of these little scale? So first of all, when the whole scale is actually completely closed, that zero mark would actually be hitting the zero. So that zero mark would read 0. So once it's open, that zero mark would be the marking point of what's the reading of distance d is going to read. So for example, if I zoom in here and I read the major scale from here would actually read 2.4 centimeters. So because the 0 is between 2.4 and 2.5 centimeters. Then again, as you could see, the tool actually has higher precision here because it actually has a little, the minor scale, the vernier scale that is actually sitting down there. And to do that, you would actually want to take the scale precision into consideration. And the equation for the tool's precision is actually written in your lab manual. So please look into those and study that. Then again, back to our original question, what is the reading here? The major scale reads 2.4 centimeters. The reason that it reads 2.4 centimeters because the 0 scale sits between 2.4 and 2.5, but it's not quite 2.5, but it's more than 2.4. So the question is, what is that little bit that is just a little bit more than 2.4? So a Vernier Caliper actually allows us to make an estimation of the last remaining digit. So right here, what you want to do is you want to find a matching scale between the vernier scale and the major scale. So if you keep looking, you can see that the 11th vernier scale matches the reading on the major scale, like Like if you take a look at that 5.5 scale, you can see that the scale from the vernier matches with the major scale. So what you want to do is whatever or wherever the vernier scale matches with the major scale, that is the point of the number that is actually addition to the major scale. So right here, you can read that the point where it matches is 5.5. So that 5.5 is actually 5.5 out of 10 from a millimeter. So you convert that into centimeters and you get 0.055 centimeters, and you add them together and you can see that the Vernier Caliper could read 2.455 centimeters without any estimation. So a Vernier Caliper is extremely precise, and the precision could actually be read on the bottom right. You can see that there's a number 0.05 millimeter down there. So this is the precision of a Vernier Caliper. So whenever you use a Vernier Caliper, you want to report the proper reading of the whole scale. So make sure to read first the major scale and then read the vernier scale, then do the conversion and then add them together. Please feel free to revisit that video if you need any revision. Regardless, in order to represent any data that was collected statistically, you also want to consider the statistics that are also important in representing data. So let's say we're dealing with random distribution, and it would actually give you some sort of this bell-shaped curve. So basically, this bell-shaped curve would actually tell you like what is the general trend of the data. So first number you want to take into consideration is the mean, which is essentially the average of all the data that you've been collecting, and the mean would actually be the representative of the whole data, and generally it would actually have the highest distribution as well according to the normal distribution. The way you do it is you sum all of your data and divide it by the number of measurement end that you have done, and from there you could actually use the mean to make an estimation of the representation of the data that you've collectively collected. And next is the standard deviation. Standard deviation is basically how spreading this thing is when you consider a set of data. So if you measure something that changes a lot, then you would get high standard deviation, and the standard deviation would actually tell you how much percentage. For example, this one area of this guy is basically 1 sigma, and 1 sigma is 1 standard deviation. So if you see the letter sigma like down there, it would actually be how big is the population away from the mean that is represented by this standard deviation. So it tells you how largely it spreads. So the smaller standard deviation, it means that the more precise you've done your measurement. So this is something you're looking into minimizing, and this can be calculated by this equation. Basically, you sum the differences between x, each collective data with the mean, and squared. You sum all of them divided by divided by n minus 1, and then take a square root. And then from standard deviation, you can actually estimate the statistical error or standard error from standard deviation that you have done by dividing it by square root n, where the small n is the number of the sample that you've been actually sampling. So for example, say you do 10 measurements, then n would be 10. And in this case, you'll be working with these statistics in this measurement class, which is an introduction. And then again, please feel free to look into any online calculator that would do this statistical calculation for you. All right, so here is the experiment part. So the tools that you're generally given is a stopwatch. And this stopwatch actually has a precision of 1/100th second, which you'll be using throughout the class. And this is a standard model. And you could also be using the Vernier Caliper. And the Vernier Caliper, as I explained, it actually has the precision of 0.05 millimeter. And this is what it looks like. and you'll be using it to measure this little cylinder. And this cylinder actually has like a hole in it, and it also has the outside and inner radius, and it also has its height. But then again, it's actually a block on the other side, so you will be playing with it throughout this class. And then again, last but not least, you'll also be playing with a micrometer. And a micrometer is something that you could potentially use to measure things down to a precision of microns. So let's go on to part 1. So first, in order to use the Vernier Caliper, you need to be able to read the scale. So the scale is just like what I described earlier. The thing is, once you turn this thing around and open it, let's say I want to measure my fist right here. So I spread out and then stick the caliper in and then clamp it on. So the distance that little gap down there is open up is going to be the size of my fist. Or another thing is, or in other words, whatever you want to measure is on that scale right there. So all you have to do is clamp it on top of the object that you want to measure, and then carefully and read the minor scale that you major and minor scale, like I explained earlier, and then do the addition. And from there, it would actually tell you the spreading of the whole thing. And the thing is, if you close this whole thing up, you can see that the 0 scale on the Vernier scale on the bottom would actually become 0. So in order to read Vernier Caliper, you would be paying attention to that 0 scale and look into the location where it's actually landing on top of a major scale. So technically you get to play with this, and then once you open it, let's redo the measurement. If I stick it on top of my hand like this, now we would actually be looking into the scale, and from there we could actually make an estimation and try to read the details from the precision. Like for example right here, the 0 scale might be a little bit hard to see, but it's is like right beyond 0.9. So let's see how we can actually read it in detail. So we know it's more than 0.9 centimeters according to this dummy large scale, but then again, you would actually want to try to match the smaller scale to see if the vernier is actually giving like the correct reading onto this guy. So right here, I will make a better vision on top of this guy right here. So from earlier, you know that it's more than 0.9. So if you take a look at the first scale, the 0 scale on the bottom, it actually sits between 0.9 and 1.0. So the question is, what is that little bit that's more than 0.9? So you want to carefully look into the scale and see where's the matching that's actually showing up on top of the here. So the Vernier scale, the 0th Vernier scale, is actually sitting between 0.9 and 1.0. So you want to try to find where the Vernier scale actually matches with the major scale. So if you take a look right there, you can obviously see that the scale is actually not matching. So you keep going until it matches. So sorry, I moved it a little bit, but you can see that the 5th scale right here, it actually matches with the major scale. So whenever the vernier matches the major scale, you can actually read. So right here, you read 0.9 centimeters plus another 5, and that's 5 out of 10. It's going to be 5 out of 10 millimeter, because the smallest scale on the major scale is 1 millimeter. So that's going to be another 0.5 millimeter in addition to whatever I was reading. So from the major scale, from the 0 scale, I read 0.9, and I'm reading another 0.05. So the reading here would be 0.95 centimeters as a reading of the Vernier Caliper. But then again, this is just an example. The Vernier Caliper that you'll be using in this lab is going to be a little bit more precise. So the precision right there is going to be 0.05 millimeter. All right. So first activity of the of this lab. Sorry for my shaky hand. Okay. All right. So you want to measure the outer radius of this little cylinder 10 times. So the way to measure the outer radius is you want to squeeze that little arm, and then once you find the length, you want to lock it using that little screw there. So that's how you measure the outer radius. Now you want to measure the inner radius. To measure the inner radius, you want to stick the other end onto it and then open it up. So that gap right there between these little two scissor parts are going to give you the reading of the inner radius. Alright, next thing you want to know is how deep is this little cylinder. So to calculate the depth of this cylinder, you want to stick the bottom end. So you see, if you open up the Vernier Caliper, there's a little bit piece in the bottom that could actually reach the bottom of this little cylinder. So what you want to do is you want to stick it down onto your little cylinder, and then a Vernier Caliper would actually give you the reading of how deep is that little hole. Then again, you could actually just read it from the major scale and the vernier scale. Please be sure to read it from centimeter scale. All right. Second part, you will be using a micrometer. So a micrometer looks like this. So first of all, you'll be using this to do a very, very, very fine measurement. So a micrometer actually implies that the precision is in the order of micron. So how big is 1 micron? Micron is 10 to the negative 6, right? So that's basically 0.0000001. So basically, it literally has 6 zeros in front of it, or maybe 5 zeros. Yeah, after the decimal points. Regardless, this is extremely precise. So in order to use it, you would actually end up having to open this little squeeze. So first of all, this thing actually measure the length that you could actually read from that little gap that you could actually open. So first of all, when you use it, you want to make sure that the 0 point is somewhere around the 0. So and then you start opening it, and once you open it, you could start reading the scale, and be sure to use the coarse adjustment, and then stick whatever you want to measure in between the gap that's open. So you want to moderately opening it, and then stick something that you want to measure in between. Let's say my 2 fingers there. How big does it read? So when you look at it, you want to look into the scales. Alright, so here's a closer look. So a micrometer would actually have some offset. It could actually be ahead of the measurement, or it might fall behind the measurement. For example, in this case, it actually falls behind the measurement, because instead of reading it starting from 0, it actually starts below 0. So please keep in mind to read the 0 point before you start reading anything out of this. And then once you record the 0 point, you want to open it, and as I said earlier, and now you would actually see measure scales. So right here, the ticks on the minor scale would actually read from 1 to 50, and there are ticks on the major scale from the top scale and the bottom scale right there. And let's see if I want to measure the length of my 2 fingers right there. What would I read? So right here, I could actually make an adjust using fine adjustment knob, which is further to the left further to the right on this video. And once it makes clicking sound. You could actually start making any reading. So you want to make space that's large enough for you to actually squeeze in, and then use the fine adjustment scale. As you can see, I wasn't grabbing the yellow part of it, but I was grabbing the gray part of it. So now it's time to read the distance. So the scale on the top is 0 and 1 millimeter. 0 and 1 millimeter. So basically, as you can see, there are scales on the bottom. So you can see that the scale on the bottom is literally, so the step between 0 is going to be 0.5, 0, 0.5, and then 1, and then 1.5. So the major scale reads 1.5 millimeter. But then again, the 1.5 millimeter is, you can see that the reading is a little bit more than 1.5 millimeter. So right now, you actually want to read what's on the minor scale. So to read the minor scale, you want to read the number that shows up on the back right. So right now, it's reading is reading 13.5. So it's reading 13.5 on the minor scale. So the major scale reads 1.5, and you have the minor scale that reads 13.5. So you could technically add these number up. So since the minor scale is 0.5 millimeter, so that 13.5 out of 50 scale is going to read 0.135 millimeter. 0.135 millimeter. So if you do the addition between the major scale that reads 1.5 with the 0.135, you could actually read 1.635 as your final reading. So right now you could report 1.635 millimeter based on this reading. And as you can see, that the last digit here is on the third decimal point of millimeter, and that is 1 micron. So the precision of this guy, if you write it down, any answer that was read from a micrometer in millimeter, you want to have 3 decimal places. And in this case, I am reading 1.635 millimeter. So if you're not clear with this, rewatch the video and then try to redo this measurement yourself. Then again, once you record the reading, be sure to subtract it with the whatever it was reading on the 0. So if it falls behind, you would get a negative set offset, and if it's actually ahead of the reading, you could actually get a positive offset that you have to subtract off, and the details of the subtraction is on the manual. So this is the actual micrometer. Again, sorry for my shaky hand. The way to use it is you want to open it all the way out, and right here you want to use it to measure the size of the bead that was given to you. So you want to make sure that it actually has enough space for the bead to fit in between the gap before throwing the bead in. So you want to open it using the coarse adjustment all the way out, and then stick the bead in. Okay, all right. So here's the bead going in. So once you stick the bead in, instead of grabbing onto the to the coarse scale, you wanna actually grab the fine scale until it clicks. So right here, I'm adjusting the fine scale, but it's actually a little bit out of camera. But here, all right. So make the fine scale adjustment for the bead to actually sit in tightly, and then from there you could actually use the reading from the scale. So right here is a little bit more than 15.5, I think. Yeah, 15.5 millimeter. So do the reading and repeat it. All right, part 3. So everyone would actually have a stopwatch on each table. Or if you're doing this module online, you could also use your application, the stopwatch application, and it on iPhone or generally it would actually have the same precision of 1/100th second. And what you want to do is you want to start a pendulum, so tilt it by 5 or 10 degrees and measure the length of the string, and then do a simple pendulum measurement and take a measurement of how long is the period of this pendulum swinging. So a period is the time the pendulum takes from getting from one spot to the same spot once again. For example, if I were to count where the pendulum starts from the highest displacement to the left, then I would be like click, click 1 period, 2 period, 3 period, 4 period, for example, and then you do the measurement of 20 periods and then make a division. And after you're done with this third part, you want to repeat this how many times depending on what the manual tells you. But then again, once you're done with this part, you get to do the fill form that actually is in the lab manual. Last but not least, please enjoy the lab.